Hi everyone, this lesson is going to be about planar graphs. Now here is an example of a graph, but we notice here that the edge from E to C crosses the edge from D to B. So the question I've got is, can we redraw this network in some way so that no edges will be crossing? And in order to make my life a little bit easier, I thought I would use this piece of software called Geogebra. So this is totally free software that you can download and use. So I've just selected here from this menu points, and as I click onto the grid I'll be inserting points. So AB, I'm going to roughly try to get the same shape as this. It just goes alphabetically. So there we go. Now once I have my 5 vertices there, I'm going to draw them a segment, a line segment between them. These are our edges. So A to B, then A to E, E to D, D over there to B, B to C, and C to E. Now, so what? I've got the same thing drawn. The nice thing about this software is that I can use this arrow here to move. If I click point A, vertex A, as I drag it around, the edges remain attached. So I can have a little bit of a play around with this and see if I might not be able to redraw this in some way. Now almost there we are. If I were to redraw, it's still the same network. It's isomorphic because I have the same number of vertices, the same number of edges, and the same relative connections between them. Now is that the only way I could transform this into a planar graph? Well, no, it's not. If I put that back where it started, I could have grabbed vertex C and moved it into here. That's only one possibility. I could have taken vertex D up here to the top left. Now, all of these different transformations, as I say, represent the same information. They are all isomorphic. Now, the nice thing about a planar graph that we've got here is that it divides the plane into distinct regions. So I have got, let's see, how many vertices do I have there? There are 5. How many edges do I have there? Well, counting around the outside, there's 1, 2, 3, 4, and then there's 5, 6 edges. Now how many, the new term coming up, how many faces are there? The faces are the distinct regions of the plane. So this is a face here. This shape is bounded. That's one face. This is another face in here. This space is bounded. So there's 2 there, but don't forget the outside one. This one is unbounded, but it's still a region of the plane. So there's actually 3 faces there. Now I don't think I've got any, I don't have colouring in, no I don't. So that's, well, that's okay. We can, oh, wait a minute. What if I do a polygon? Oh no, don't worry about it, I'm getting crazy. So we can just, oops, we can just count these up. Now where did my notes go? Let's just push the notes across a little bit to the side. There we go. I just want to write something down here. Give myself a bit more room. And where did, oopsie, didn't mean that. There's my graph. That's easier to see now. Now, how many vertices did I have? There were 5 of them. How many faces did I have? There were 3 of those. Remember, the faces are the regions of the plane. And how many edges do I have? I believe we had 6 of those, 4 around the outside plus 2 in the middle, 6 of those. Now, if we go V plus F minus E, 5 plus 3 minus 6, that gives us 2. How interesting. Now, let's just try another one. Let's just move. Oh, why did that get so big so suddenly? Let's try going over here. Now, what what about if I tried doing something crazy? I'm going to draw a little square there, and then I'm going to draw a little square there. So I was careful to use the grid to get those as squares. Now I'll draw my edges. Now this won't be planar to start with. So there's a square. There we go. Now I'm going to start connecting the two squares. Hopefully that looks like a cube in 3 dimensions. And this is one of the questions that Euler looked at. Euler said, Euler was the mathematician who devised these ideas. Euler said, I wonder if I could make this 3-dimensional surface into a planar graph. And the answer is yes, we can. So what I'm going to do is I'm going to take this little top square, and it's going to get a bit squeezy, and squeeze that right in tight. I know it doesn't look like a cube anymore, but that doesn't really matter, as long as the edges remain connected. Now if I bring this one up to here, there we have a planar graph. Let's make it look a little bit neater. Put that one there, put that one there, put that one there. It's a bit wonky donk, but hey, it's close enough. There, that's nice, that's nice. So this is still exactly the same planar graph that we had. Now, how many vertices are there? Let's just put that back to where it was a moment ago. There's the notes. There's the graph. Let's make sure we can see the graph. So let's we did that first one. That was good. That was our first one. Now let's do this one. How many vertices did we have here on this cube? Well, let's count them up. 1, 2, 3, 4, 5, 6, 7, 8. How many faces were there? Well, there's 6 faces on a cube. Let's check. So we've got 1 face there, 2, 3, 4, 5, and then the outside region, that's the 6th face. So there are 6 faces still. Well, how many edges were there? Let's count around the outside. 1, 2, 3, 4. Let's count the inside. So 5, 6, 7, 8, 9, 10, 11. There are 12 edges. Now let's try that little rule again. What was that rule? V plus F minus E. There are 8 vertices plus 6 faces minus 12 edges. 14 minus 12 is 2. It came to 2 again. Now, this thing is called Euler's formula, and his name is spelled E-U-L-E-R. Euler's formula. And that is the vertices plus the faces minus the edges always equals 2, as long as you have a planar graph. Remember, a planar graph is one like this, where none of the edges cross over each other. Well, I hope you've enjoyed this lesson. I encourage you to have a look at this software, Geogebra. Very handy for doing these types of network diagrams without drawing lots and lots of things all over your page. Thanks for watching.